In this video, we are going to learn, in a simple and practical way, the concept of relative humidity of the air and its close relationship with the cooling process in air conditioning and refrigeration systems. Understanding this principle is essential, since humidity not only influences people's thermal comfort, but also affects equipment efficiency and the preservation of products stored in cold rooms. On the screen, we see a mass of air. Within it, small blue circles are shown, symbolizing the amount of water vapor contained in that volume. If the air mass is so saturated that it cannot hold any more vapor, we say it has reached 100% relative humidity. At that point, any additional amount of water vapor cannot be absorbed and condenses in the form of droplets. Now then, what happens when the temperature of the air mass increases? Air, being a gas, responds to heat in a predictable way. Its molecules begin to vibrate more intensely, separate, and the air volume expands. As the volume increases, the air gains a greater capacity to store water vapor, even if the original amount it contained does not change. In this scenario, relative humidity decreases. For example, if it was previously at 100%, after the temperature rises, it may drop to around 66%, because now there is more available space for the air to accept additional vapor. It is important to clarify that the total amount of water in the air mass has not changed. What has changed is its capacity to retain moisture due to the variation in volume. This explains why on warm days the air can absorb more water vapor, and why, if there is a nearby source of humidity, the air tends to capture it more easily. Now let us observe the opposite. When that same mass of air passes through a heat exchanger or evaporator of an air conditioning or refrigeration system. In this process, the temperature decreases. As it cools, the air molecules lose energy, move more slowly, and the volume of the air mass contracts. As a consequence, the air reduces its ability to retain water vapor. If at that moment the relative humidity was already close to 100%, the decrease in volume will cause the excess vapor to have no space to remain in a gaseous state, and it will be released in the form of condensation, resulting in the formation of small water droplets. This phenomenon is exactly what happens in air conditioning systems. When ambient air comes in contact with the cold surfaces of the evaporator, the humidity condenses and is removed in the form of water. Proper control of humidity in this way can also reduce the sensation of stuffiness. In cold storage rooms or refrigerated chambers, controlling this same principle ensures that stored products maintain their properties better, avoiding excess humidity that could promote mold growth or spoilage. In summary, relative humidity does not depend solely on the amount of water vapor present in the air, but also on the temperature and therefore on the air's capacity to retain that vapor. Understanding this interaction is key both for designing efficient air conditioning and refrigeration systems and for properly managing the preservation of food, medicine, or any product sensitive to environmental conditions.